本日最初のテーマは、ファイルシステムファザーを使用したカーネルエクスプロイトのハンティングについて、キム・ドンヒさん、ホン・ソンピョさん、ウォン・ヨン・ジョンさん、ホージン・ジョーさんからご紹介をいただきます。キムさんたちのほとんどは韓国の現役大学生、セキュリティエリートを育てるベスト・オブ・ザ・ベストのプログラム、セキュリティコンサルティングトラックを通じて知り合いました。今回のテーマについて動画をいただいておりますので、まずはご覧ください。
Hello, I'll start our presentation on the hunting kernel exploit with file system fuzzer. First of all, let me briefly introduce the table of contents before starting. For the beginning, I will briefly introduce our team and why we select this topic. Let me tell you how much the vulnerabilities affect various OS. Then I'll tell you in the order of Triage Monitor, analysis crashes, and kernel exploitation. This project was conducted in the Security Talent Training curriculum called BOB. There are 2 mentors and 1 PL. I'm in charge of the PM, and there are 3 team members. There are various file systems in the world. However, there are a few cases of attacks through the file system. This is because it is a weak model. At this point, you might think, isn't it already root privileges to mount the image? However, if you put in a USB and plug into a PC, it becomes auto-mount without any need for root privilege. At this time, if the crafted image is mounted, kernel panic can occur. In this way, there was an attack model through USB. And also, we use Janus. We developed a web monitor and analyzed one day and successfully leaked memory. At last, we exploited kernel through 0 day. There are various OSs in the world, and there are many file systems used for each OS. But file systems are large and complex, making it difficult to find bugs. However, file systems are managed in kernel space, so they can be good attack surfaces. In addition, kernel interaction is possible in user mode. Each process access one file system, so UAF or race condition bugs can occur frequently. As shown in the below, the file system is difficult to audit because the line of the code is long. Janus uses the Linux kernel library. LKL is a library of kernel at the application level. It is generally used to lightly emulate the kernel with QEMU. LKL is not a kernel. Sources are organized in Linux libraries, separated from the kernel version. So the version of LKL is always lower than the kernel version. The reason for using LKL is to recover quickly and attach AFL when fuzzing. First, remove the metadata from the image. Second, bound with mutated image and metadata. Finally, operate a syscall that reads image files. This way, it operates at 2 dimensions. The file system looks for files by inode as metadata, because metadata information is mutated and a crash occurs. Even if data is mutated, it's useless. In this way, an image is created and system calls are called randomly to induce the kernel to touch it wrong. Therefore, it occurs when mount, sync, and unmount. Our targets are ext4, f2fs, and btrfs, which are file systems that are auto-mounted in Ubuntu. Especially ext4 is auto-mounted in many OSs. As the most basic file system, there is metadata in the block based on inode table, and fuzzer will mutate this. btrfs is light, efficient B3-based memory management and features automatic defragmentation. btrfs is optimized for SSD and allows you can use it like a single SSD, although multiple plugged in. F2FS is a file system optimized for NAND flash created by Samsung for flash memory. When the price is acquired by the actual Gerodium company, the price is set as follows, and the bugs they want should remain long. File systems are managed individually, so even if a bug is patched, it is reflected in the kernel rate. When applying the found CVs, a bug occurred in various OS as follows: 3 in Ubuntu, 4 in Groom OS, 25 in Harmonica OS, and 2 in Red Star OS. Then I'll show you what causes kernel panic when USB is plugged in on a smart TV. The video shows that an existing crash is affecting the device you are using. The vulnerability is CVE 2018-10879, and the target TV is a Samsung TV released in March 19th. The corresponding OS is Tizen 5. Victim is using a TV, and the attacker is a malicious USB plus the USB into the TV. Afterwards, kernel panic occurs and you can see victim's TV freeze. If debugging is possible, I have seen the possibility of exploit. We ported it to the version 5 of the kernel and then uploaded it to 5.3, but there were many duplicate crashes and many invalid crashes. Therefore, Triage was developed and the crash file was changed to amount of image, and the Kazan memory analysis plugin was installed there. Reproduced through QEMU, unit crash was classified according to the type of bug and then saved in DB. Efficiently checked and managed through the web monitor. You can remotely set and run file system fuzzers and check the crash list. This is overall structure of the triage and monitor. There are a total of 16 CVs reported by us. Some of the reported CVs will be explained by our team members.
Now, let me explain the CVE ratio we reported and detailed analysis of CVE. The following is the percentage of CVE we obtained per file system. The number of CVE that we reported was total of 16, which is small, but it can be seen that they occupy a significant portion of the CVE ratio for file system. This means that there is not much research on the vulnerability of the file system. It would be nice if additional research on file system was done in the future. So, since the final goal of our analysis of crashes is LPE, we internally scored each crash from 1 to 10 depending on the extent of exploitability. Now, I will explain the analysis of each crash type. First, null pointer dereference vulnerability. The ext4 mtdir function check if there are any files in the directory when executing a command that deletes a directory such as rmdir. The vulnerability is structure pointer called bh in the ext4 mtdir function. If the pointer becomes null, the location of b data cannot be calculated. If the next loop fails to find next entry during the loop of the function, if the return value of the ext4 read dir block function becomes 0, then the next loop is a null pointer reference vulnerability that occurs because the location of PHP data is not calculated. For the exploit of the null pointer dereference, you need to assign memory to a low address. However, the zero address protection protects the null region. So if you use the null pointer dereference vulnerability, you can only do kernel panic. So it is not much different from turning off the PC. So we gave 1 point internally. Next, slab-OB vulnerability. The variables old size and new size is set during the process of setting up entry for the ext file system. These two variables are defined as size_t. Among them, the value stored in old size is calculated through a function called LE32 to CPU. An unexpected large value may be set due to the difference between the 32-bit data type and the 64-bit data type in 64-bit OS. This is vulnerability that occurs when there is no code verify the value after that, and very large area from the first bar pointer memory initialized 0. I wanted to use this vulnerability, but the memset itself was only 0, and in order to use another method, I had to consider other side effects that occurred when the value was initialized to 0. So I gave it 4 points internally.
Next is the UAS vulnerability. This is a vulnerability caused by the BTRF's queue work function. Free work queue structure comes into the function, and vulnerability occurs when referring to work queue height. If you know free timing, then you can easily exploit it by pushing another object. Also, the work queue structure has a meaningful function pointer. So if you have triggering part of function pointer, control flow hijacking is possible. So I gave it 8 points internally because it is very exploitable.
To exploit this vulnerability, we need to use heap spraying technique. Before spraying the kernel heap, there are a few things we need to know. First, memory allocation and management are done indirectly through syscalls. Secondly, each syscall has an allocatable minimum and maximum size. Therefore, there is possibility that we will not be able to allocate objects of a certain size. Finally, since the kernel heap is managed through syscalls that are called by multiple processes, various variables exist when spraying the kernel heap. So there are several conditions for heap spraying. It must be user callable syscall, and memory allocation size must be adjustable, and the allocation value must be controllable. And there were some syscalls that struggle for these conditions. Now we will explain the overview of the zero-day vulnerability that we found, the part that was blocked while developing the exploit, and how we solved it. First, the vulnerability is a UAF found in the BTRFS file system. In BTRFS, the kernel work queue function is used for async operation, and our work queue are released by the closed function, which called during the unmounting process. However, if the async option is set in the input function, called in the same closed function, it enters on specific routine and usually after free occur, referring to the work queue that already has been free. We had to do heap spraying to exploit this vulnerability, but there were several problems. First, due to the property of the vulnerability, it was not possible to exploit the general UAF method of free, reallocate, reuse. Since everything is done within closed tree, the problem was solved by triggering the vulnerability by spraying the kernel heap through a background process. Second, the size of target structure was 16 bytes, which was too small. The heap spraying technique described earlier could not be resized or had a header of 18 bytes. So, a heap spraying technique was needed. At this time, we discovered the heap spraying techniques used in the presentation of BVX 2018 Linux kernel vulnerability exploitation. These techniques used on ZX80TR syscore, and the allocation size can be set from 8 bytes. However, when the syscore that terminated, the allocated memory was freed, so heap spraying was not possible with the syscore alone. Typically, the minimum size of kernel memory allocated by the ZX80TR syscore is 16 bytes, which fits the spraying size we needed. When calling syscore, the kernel memory is allocated through kmalloc function, and the article input value is copied to the kernel memory through the copy from user function. However, after the syscore operation is finished, the memory is deallocated, so we needed a way to make sure that deallocation does not happen. So, in this presentation, Vitaly used a memory deallocation delaying technique through the user port FD syscore. Briefly, after setting the memory address to be copied to span between two pages, when a second memory page is referenced, a page fault can be occurred by user port FD. Falls into articles routine. In the routine that called later, add code that delays kernel memory deallocation through the sleep function to prevent memory deallocation from happening. Visualizing this, when calling the copy from user function in the ZX80TR syscore, user port FD is set between A and B of the user memory, where the memory copies will be made. It then calls syscore to allocate 16 bytes to the kernel memory. After allocating kernel memory, ZX80TR copies the string A from the specified user memory to kernel memory, as shown in the figure. After copying A string, while copying B string, a page fault occurs because user port FD refers to the set memory address and calls designated callback function for exception handling. And the designated callback function, the thread sleeps for the specified time. Therefore, memory allocated through the ZX80TR syscore remains in the kernel memory without being freed for a specified period of time. In this way, we were able to reallocate the freed work queue structure in the closed tree using this technique and modify it to an arbitrary value. Since we have to pull control over the pairs of the work queue struct, we started further analysis of how the fields in the work queue structure are used in operation after the BTRFS queue work function. And through the analysis, it was confirmed that the following actions were performed. First, it inserts a structure pointer into the work queue through insert work function that is called upon unmounting. Second, a worker thread is created through the wake-up worker function called from the unmount thread. Third, it calls the select task RQ function pointer that exists in the structure field to specify the CPU number to be used by thread. At this time, the select task RQ function pointer is referenced using the field of the work queue structure that was controlled through the previous hip spring technique. So it is possible to manipulate the pointer in the environment where the kernel protection technique is off. Therefore, by analyzing the following structural reference flow, we were able to match the structure field values references by each routine and finally make the select task RQ function pointer point to article record. So it was possible to control RIP through vulnerability as follows.
First, check the user ID, try to read the secret file, and run the exploit code, and sometimes later, the shell opens, check the user ID. It's root privilege, and you can read the secret file. If you have any questions, please contact us at the email address below. Thank you.